All right. Thank you, Mathieu, for the introduction, and let me especially thank the organizers for the invitation to this great conference. I have to add that I'm also a Max Planck Fellow at Max Planck Institute of Quantum Optics in Garching in Germany, and many of the experiments I'm reporting on have been carried out there. As a short introduction, let me make a trip inside matter, and you see when you get deeper and deeper inside matter, not only the spatial dimension shrinks, but also due to the quantum states involved, the time scale on what processes happen is getting smaller and smaller. So we end up on an attosecond time scale for electronic processes on the atomic scale, and attosecond physics in the end is the observation and the attempt to steer electronic processes. So if I go through my talk, I will first introduce the method that we are using. It has been addressed by the previous speaker, Chang-Hee Nam, but I will make a very short or brief introduction to this. And then I will talk about electron dynamics in atoms. And if you look at the title of my talk, it looks like for a solid-state physics or surface science community, but you will realize that especially the method that I'm using comes from AMO, atomic and molecular optics, but also, well, I don't know why this happens. Okay. The examples of electron dynamics in solids and layered systems will bring us into a regime where not only solid-state properties like band structure and so on play a role, but also the atomic properties. So let me start with the streaking method. We are normally using millijoule lasers at a kilohertz repetition rate that provide something like 25 femtosecond pulses, which are still too narrow and therefore too long in time, narrow in bandwidth and too long in time for what we need. So we send them into a gas-filled capillary in order to broaden the spectrum by cell phase modulation. And what we get out is a very broad spectrum reaching over the whole optical visible regime. And we end up with pulse durations shorter than 3.5 femtoseconds, which is less than 2 optical cycles. This is very important because, here a picture of the lab. You see the red pulse getting in is getting more and more white. And we need these very short pulses because in the process of high-order harmonic generation, which has been introduced by Chang-Hee Nam, where the laser pulses interact with a medium and generate high harmonics, it's very important to have few cycle pulses, which you will see in half a minute. So we shoot on a gas target, have the beam propagate. You see the harmonic beam has a lower divergence due to the shorter wavelength. So we get a double beam. And now if we use a multi-layer mirror, then we can select the highest photon energies from our harmonic spectrum. So this is the harmonic spectrum, and you see if you use a few cycle pulse, then the cutoff, the highest energy region of this harmonic spectrum is not modulated or barely modulated anymore. And therefore, if you do spectral selection with the reflectivity of a multi-layer mirror, you can select a single isolated attosecond pulse. And now in this setup, we use a double mirror system where the inner mirror, which is the multi-layer mirror, can be moved with respect to the outer mirror so that we can introduce a time delay between the attosecond pulse and the residual infrared laser pulse that has previously generated the attosecond pulse. So you have a perfect synchronization and can introduce a delay between these pulses and then focus these two pulses on a target and do photoelectron spectroscopy by measuring the energy of the electrons that pass a time-of-flight drift tube. So this is what happens. The electron is kicked out. The electron is kicked out by the extreme ultraviolet attosecond pulse and feels an additional momentum coming from the dressing field of the laser. If we look at this in time, you see that when the ionization takes place at different instants of time, so this may be a cloud of atoms or a solid or whatever, then the electrons set free feel different phases of the dressing field. So they end up finally at our detector with different energies, and we can map time to energy with this method. Wow, this is kind of magic here. So now if we scan the attosecond pulse through the dressing field, then the electrons that are emitted from an atom, you see here the electron spectrum, which mimics the attosecond pulse, is highly modulated, moving up and down in energy. And now this is what we get here, a spectrogram where all these spectra at different delays are put together. We call it a streaking trace. And this is the famous horse. So when you go to an ultra-fast conference, you always see this famous picture of Muybridge, who wanted to answer the question whether or not a running horse loses ground contact at some point of time. And he was stringing together snapshots and then was kind of doing slow motion so he could resolve the process. And this is what we do. We take snapshots at different delays, string them together, and can reconstruct the process. But we are not only interested in measuring the field, the dressing field, which obviously we can do, and the pulse duration of the attosecond pulse, which can be done in algorithms like Frog, as has been mentioned before. But we also want to look at the underlying physics of the photoemission. And if you have here a model system of any type of solid, or it can also be different energy levels in an atom, you see you can do valence photoemission. You can, if you have enough photon energy, do core level photoemission. You can look at the process like Auger decay or shake up, or even a convolution of more of these processes. And when you have such complicated processes, it may be very difficult to investigate the process underlying only by the spectrum of the electrons that come out, but you would like to have a time-resolved method, and you can do the streaking method with all types of these electrons and conclude on the processes that are previous to the emission. Now, as I said, if you have enough photon energy, it may be interesting to have more photon energies, and here is a machine, the laser linear coherent light source at the Stanford Linear Accelerator Center, where you can go to higher photon energies. So high harmonic generation is more or less restricted to a few hundred electron volts. If you go to more than, let's say, 150 electron volts, there are so few photons that experiments get extremely difficult. Now at this machine, where electrons are accelerated in a linear accelerator and then sent through an undulator, people have found a very smart way to generate ultra-fast pulses. They send the electron bunch before the undulator through such a foil, which they call slotted spoiler. Why spoiler? Because the electrons that pass the gold part of this foil lose coherence, and therefore you do not have free electron laser emission of this part of the bunch. So only a very little part of the electron bunch is lasing, and therefore you can get down to the femtosecond regime with these pulses. You can go to very, or let's say to high photon energies up to 10 kiloelectron volts, but the problem is that you have all kinds of jitter with respect to a reference laser, because the electrons that you generate upstream at the beginning of the accelerator, of course, have to go kilometers of acceleration, and therefore all thermal and whatever disturbance goes into it, so you have any kind of jitter there, and you need single-shot measurement, which is not so easy. So if we again look at photoelectron generation with these X-rays, you have the free electron pulse, you have the spectrum of the electrons coming out from an atom, and then you see you have arbitrary jitter, and one of course can conclude from the final spectrum, just like in the streaking method, but it's not so easy. So people have set up a very smart system where you put an array of 16 electron time of flight detectors on a wheel, and then you use a circularly polarized dressing laser field. And what happens here can be shown in a very simple way. You have here the two components of the circularly polarization. This is the actual field of the laser pulse. And you can imagine if you have photoelectron emission in this kind of dressing field, then to all directions you get a different way of streaking, which you then detect. So the detection is like modulated by the hands of a stopwatch. And this is what happens if you have one single photo line, which is then detected by the detectors, and you add a streaking field, then it's shifted, and we did a measurement, and you see these are the spectra kind of over the 16 detectors, and from shot to shot, so each circle is for a single shot, you see the modulations. And if you look deeper in these modulations, you see here are the 16 streaked spectra of one pulse. You can get all the information that you need for the reconstruction of the pulse. And in the previous measurement, we saw that out of 10,000 shots, you get something like 50 or 60, which are really below 1 femtosecond. So what you can do now with this machine is that you do pulse tagging. So you measure in parallel to any experiment in AMO, and you tag the pulses and you sort out those who are shorter than 1 femtosecond, and therefore you're able to do a sub-femtosecond experiment with multi-kilohertz, with a multi-kilohertz source. Going back to our high-order harmonic generation source, years ago we did an experiment on neon where we looked at two photolines in parallel. And we were looking at the 2S and 2P photolines from neon and then did the streaking. And we saw that the two photolines, the two spectrograms, the two streaking spectrograms were delayed, and we could measure that this was about 20 attoseconds as a delay in the photo emission. And the reason for the delay is intrinsic, like the Eisenbutt-Wigner Smith delay, the Coulomb laser coupling, plus the difference in energy of the two electrons coming out. But still, all these contributions do not add up to 20 attoseconds as we measured here, and we are not yet completely clear what other contribution or what error or whatever is responsible for that. Jang-Hee Nam has shown measurements in helium. Helium is a very nice atom because it's so small and can be modeled, and we were also looking into helium, especially into the so-called shake-up process, and this is a project led by Martin Schulze. So if you look at the photoionization with an extreme ultraviolet pulse, then you see what happens when electron is emitted. You have to shake down the other electron, is deeper bound. And also, you get the so-called shake-up, where this deeper bound electron goes to a higher state, and the energy that you need here is reduced from the outgoing electron. So you again get two photolines, and if you streak these photolines, you should see a delay between these two lines, which should come from the correlation of the two electrons in this shake-up process. And we did the measurement and compared it to simulations done in Burgdorfer's group in Vienna. Here, this is the simulation for the Eisenbutt-Wigner Smith delay for the direct photoionization. And now if we add the time delay between the direct photoelectron and the shake-up photoelectron, which we measured, you can see here we measured at different photon energies with different bandwidths given by the multilayer mirror that we have, and therefore with different attosecond pulse duration. And we can measure certain delays, and I think it's very nice that the calculations that have been made in Vienna on the shake-up very nicely reconstructs this delay that we have. So to show a little bit inside, so what do we have? We have the Eisenbut-Wigner Smith delay, which is nothing else than the scattering of the outgoing electron on the ionic potential. We have the Coulomb laser coupling, and if we now look at a shake-up photoemission, we have this observed delay for the shake-up, and what is missing here must be the correlation time of the two electrons involved, and depending on the energy, we get something like 5 and 12 attosecond for this time. Now passing on to solids, what do we see here? You see a sample and an XUV pulse kicks out an electron, and the electron that arrives at the surface feels the near-infrared dressing field. And I will come back to the question at what point the electron feels the near-infrared field, because it's maybe a little bit too sloppy to say at the surface it feels the dressing field. What happens, and you of course get the streaking spectrogram for this electron. What happens if you have two different types of electrons, for example, a core level electron and a valence band electron? They may arrive at the surface or may travel at different speed, arrive at the surface at different instants of time. And when you do the streaking with these two electrons, then as we saw in the atomic case, the spectrograms may be shifted, and the shift in time of these two spectrograms is exactly the shift or the difference in arrival time at the surface. Now, if we look at tungsten 110, you can see here the attosecond pulse, the electric field of the laser, the vector potential in the end that makes the modulation, and we compare a 4F core level electron and those from the Fermi edge, and we can measure the two spectrograms, look at the delay, and can do a timing analysis, and especially if you look at the zero transition, you see very nicely the delay, but the whole spectrogram carries this information, and therefore you get a very accurate measurement out of this. So this was already done some years ago in tungsten, and you see the measurement was not so nice and clean as we have today. Also the error bar was rather big, 110 plus minus 70. Now we were able to reduce the error bars, and we were since then trying to find out what was the reason for this delay. And a couple of theoreticians also were looking deeply into this question. And there were in principle two main ways to explain the difference. The one was the difference in spatial localization of the initial state wave functions. So if you look at the delocalized conduction band electrons, it may be that only this part of the wave function counts when you get out. And you have the well-localized core level electrons, or surface states where the electrons are localized well at the surface may play a role. And the other explanations mostly come from propagation effects of the escaping electrons. So if you look at the time difference when they come to the surface, it should be the pathway, the inelastic mean-free path of the electrons from the core level divided by the velocity of these electrons minus the place where the conduction band electrons come from, the inelastic mean-free path, divided by the velocity of the conduction band. And of course, the velocity of these two electrons should be dominated by the conduction band, by the band structure. And therefore, we were looking into magnesium, because magnesium is a cool test case because it has a truly delocalized conduction band, which is not the case for tungsten. And it has very well localized 2p core level electrons. And even more important, it has a free electron-like final state band structure, which makes our life easy in this case. It's challenging because it's reactive, and as you can see here or cannot see here, it has a very low density of states in the conduction band, so we have to multiply this by a factor so that we can compare the two streaking traces. And what we found out is that the delay of the conduction band and core level electrons in magnesium vanishes, which is in perfect agreement with the free electron propagation limit, because the difference in the penetration, in the depth of in the inelastic mean free path, and the difference in the speed cancel out completely. So this is in discrepancy with theories that emphasize the role of the initial state localization. But now we have the difficult job to see what is the influence of the band structure. And colleagues from San Sebastian in Spain, from Petru Bejo-Edrenik's group, Kasansky and Krasovsky and all these guys helped us to calculate, or they did not help us, they did the calculations, of course. They calculated the band structure and looked into the group velocity of the electrons. And now, of course, it's important to test this at different photoelectron energies. So we need different energies for the harmonics. And we did this by using different mirrors, selecting different parts of our photoelectron spectrum generated by high harmonics. And if you look at the blue line, which are the simulations for free electron-like propagation, and compare it to the blue and green circles, you see that we're close, but we're not exactly on this line. You see, secondly, that for different crystal orientations, blue is tungsten 110 and green is tungsten 100, we get basically the same results, which is interesting because the two different orientations have two different band structures. And you see that we're funnily off here at the 135 electron volt photon energy, which is not yet clear why this happened. Please ignore, due to the few time which we have left, the red line. Just at the end of my talk, I would like to go through electron dynamics in layered systems. Of course, we were very interested in the influence of propagation effects. How much do they count? And we had the idea to put a well-defined number of add layers on our tungsten substrate, and we were choosing magnesium on tungsten. You see 1, 2, 3, 4 add layers, and then kind of watch the electrons pass through a different amount of monolayers. And you can see here, this is the delay between the tungsten 4F and the magnesium 2P, which comes from the add layer. If you have one monolayer of magnesium and tungsten, and here if you have 4 monolayers. So of course the delay increases, and it increases linearly, which is pretty nice because it is expected. So you can, from this, really see how the electrons pass one monolayer after the other. But this is not the only result we get from this measurement. But as I said before, it's very interesting how deep does the dressing field insert the solid, right? So normally you have a certain penetration depth, and this is what is interesting for us. So we looked here at a model. You have here the tungsten, you have the magnesium overlayers, and we find, so to say, an effective near-infrared screening length. And you don't have to go into the details of the calculations, but just look at what we see here. We have a one-dimensional model where we assume a exponentially decaying electric field, and Christoph Lemel in Vienna made calculations, 3D calculations, so this should be the real value of the electric field as it penetrates from the vacuum into the magnesium add layer. And if we compare from these models our delay of the electrons with the different assumptions, we see that we get a screening depth of about 2 angstrom, which is in principle, one layer, one atomic layer on the surface. And with that, I would like to mention the colleagues who are working with me on these projects and the collaborations, and thank you for your attention.
Thank you very much. We have a few minutes for questions.
Here. Yeah. I repeat the question. The question was if I can comment on the role of surface states. If you have surface states, of course, the electrons are localized at the surface. That means that the inelastic mean-free path, which we assume, does not count, but you just have the electrons coming from these surface states. So we're at the moment looking at systems where we can have surface states and also where we quench surface states. For example, it is known that if you put a monolayer of helium on a substrate, you quench the surface states, so you could compare that. But this is a little bit of a tricky thing because one problem with our detection method is that we have a pretty high opening angle of detection. And all this, like the quenching of surface states, is known for the decay vector in the orthogonal direction. So we are at the moment setting up an angle-resolved time-of-flight detector so that we compare this, and then we think we would be able to make a kind of measurement where we can conclude on the effect of these surface states. But for me, it sounds logical that if you have a system where, let's say, the waveform of the electron is delocalized and you kind of integrate over a certain depth where the electron comes out, it must be a difference than, on this time scale, it must be a difference than if you have the electrons localized in a surface state. But this is, of course, one task to do for us, to see the difference.
Any more questions? I cannot see here because I have this light shining in my eyes. More questions? Well, if not, let's thank all the speakers of this ultra-fast science session. I think we are well on time, so we come back here at 4:30. Correct?
We have already announcements in the slide. So for those who haven't signed up for the Thursday night banquet, please come forward to make your own selection of preferred food. And tonight from 9 to 10, we'll have a mini concert of string quintet. And after the quintet, we'll have a mini bar and infinite supply of drinks. So let's enjoy the coffee break and then come back in 25 minutes. Thank you.